In 1995, a team of astronomers made a discovery so unsettling that many of their colleagues refused to believe it. Using data from galaxy surveys that had taken decades to compile, they realized that Earth, the Sun, the entire Milky Way galaxy, and everything within roughly 1 billion light-years of us exists inside what can only be described as a cosmic hole, an enormous bubble of mostly empty space carved out of the universe like someone took a spherical bite from the fabric of reality itself. We're not talking about a black hole or some exotic phenomenon from the edge of the cosmos. We're talking about where you are right now, reading this, living your life, completely unaware that you're floating inside one of the largest known voids in the observable universe. A region so vast that if you somehow traveled at the speed of light, it would take you roughly 2 billion years to cross from one side to the other. That's not a typo. 2 billion years at light speed. The Milky Way's usual neighborhood should contain about 20,000 large galaxies. Instead, we're surrounded by a cosmic ghost town, with maybe a few thousand scattered throughout this immense emptiness. And here's the really disturbing part. This discovery might explain why our measurements of the universe's expansion rate have been wrong for decades, why cosmologists are currently experiencing what they call a crisis in fundamental physics, and why we might need to completely reconsider our understanding of how the cosmos works. But before we can understand what it means to live inside a cosmic void, we need to go back to when astronomers first realized that something was very, very wrong with our corner of the universe. The story begins not with some dramatic telescope observation or brilliant theoretical insight, but with decades of tedious, unglamorous work. Throughout the latter half of the 20th century, astronomers developed an obsession with mapping the positions of galaxies. Not just a few dozen or a few hundred, but millions of them scattered across the sky. The goal was ambitious and simple: create a three-dimensional map of the universe's large-scale structure. To understand how they did this, you need to know that when astronomers look at a distant galaxy, they can measure something called its redshift. This is the degree to which the galaxy's light has been stretched toward the red end of the spectrum due to the expansion of space itself. The more red-shifted a galaxy appears, the farther away it is and the faster it's moving away from us. By measuring the redshift of millions of galaxies in different directions, astronomers could determine not just where galaxies are in the two-dimensional sky, but how far away they are in three-dimensional space. It's like taking a flat photograph and turning it into a hologram. This work required enormous telescopes, sensitive instruments, and thousands upon thousands of hours of observation time. Through the 1970s and 80s, various teams around the world conducted surveys with names that sound more like banking institutions than scientific projects. The CFA Redshift Survey, the Las Campanas Redshift Survey, later the 2-degree field Galaxy Redshift Survey, and the Sloan Digital Sky Survey. Each one added millions of new data points to our map of cosmic structure. What emerged from all this data was nothing short of spectacular. The universe, it turned out, is not smoothly distributed. Galaxies are not scattered randomly through space like stars in the night sky. Instead, they're organized into an intricate pattern that astronomers call the cosmic web. Picture soap bubbles pressed together in a sink. The soap itself forms thin films between the bubbles, creating a delicate network of surfaces and filaments. The insides of the bubbles are mostly empty air. The universe's large-scale structure looks remarkably similar. Galaxies cluster along vast filaments and sheets of matter, cosmic superhighways hundreds of millions of light-years long. Where these filaments intersect, you get massive galaxy clusters containing thousands of individual galaxies packed into a relatively small volume. These clusters are the most spectacular structures in the universe, containing more mass than 1,000,000 Milky Way galaxies. But between these filaments and clusters, you find the voids, enormous bubbles of mostly empty space, nearly devoid of galaxies, like the air inside those soap bubbles. These voids are not completely empty. There are some galaxies inside them, but far fewer than you'd find in a typical region of space. If the average cosmic neighborhood contains a certain number of galaxies per cubic billion light-years, voids might contain only 10 or 20% of that number. By the mid-1990s, astronomers had identified hundreds of these voids scattered throughout the observable universe. Most of them measured somewhere between 100 and 300 million light-years across. They were strange, fascinating features of the cosmic web, but they were just features. Interesting details in the universe's architecture, but not particularly relevant to our daily lives or our understanding of fundamental physics. After all, we weren't inside one of them, or so everyone thought. In 2013, 3 astronomers named Ryan Keenan, Amy Barger, and Lennox Cowie published a paper that would fundamentally challenge our understanding of our place in the cosmos. They had been carefully analyzing galaxy distribution data from the Sloan Digital Sky Survey and other sources, focusing specifically on our local cosmic neighborhood. What they found was disturbing. Out to a distance of roughly 1 billion light-years from Earth, there was a significant deficit of galaxies compared to what you'd expect based on the average density of the universe. This wasn't just a small statistical fluctuation or an observational artifact. The underdensity was substantial, persistent, and extended in all directions. We weren't just near a void, we were inside one. And not just any void, but one of the largest known structures of its type in the observable universe. The void they identified, which came to be known as the KBC void after the initials of its discoverers, extends roughly 700 million to 2 billion light-years from Earth, depending on which direction you look and how you define its boundaries. To put that in perspective, the entire observable universe is about 93 billion light-years across. Our void accounts for a significant fraction of the space we can actually see and study in detail. The density deficit inside the KBC void is not subtle. Compared to the average cosmic density, our local region contains somewhere between 20 and 50% fewer galaxies than it should. Imagine living in a city where half the buildings were missing. The skyline would look fundamentally different, and you'd immediately notice something was wrong. That's essentially where we find ourselves cosmically speaking. Now, you might be wondering why this wasn't noticed sooner. After all, astronomers have been mapping galaxies for decades. How could we have missed the fact that we're inside an enormous hole in space? The answer has to do with perspective and the gradual nature of scientific discovery. When you're inside something enormous, it's difficult to see its full extent. It's like trying to recognize that you're in a valley when you're standing at the bottom. You can see the hills around you, but understanding the full topography requires stepping back and looking at the bigger picture. Early galaxy surveys didn't have enough data points at large distances to recognize the pattern. They could see that nearby space seemed a bit underdense, but without mapping galaxies out to 2 or 3 billion light-years in all directions, there was no way to know whether this was just a local fluctuation or part of a much larger structure. The realization came gradually as surveys became more complete, and astronomers developed better statistical tools for analyzing large-scale structure. By the early 2000s, several research groups had independently noticed something odd about our local cosmic neighborhood. Papers published between 2000 and 2010 with titles like "The Local Hole in the Galaxy Distribution" and "Evidence for a Local Underdensity in the Universe" began pointing toward the same conclusion. But it wasn't until Keenan, Barger, and Cowie's 2013 paper that someone explicitly claimed we were inside one of the largest voids known to exist. The initial reaction from the scientific community was skeptical, which is exactly how science should work. Extraordinary claims require extraordinary evidence, and claiming that Earth occupies a statistically unusual position in the universe is about as extraordinary as claims get. Many astronomers pointed out potential problems with the analysis. Perhaps the data was incomplete in certain directions. Perhaps there were systematic errors in distance measurements. Perhaps the boundaries of the supposed void were being defined in a biased way that exaggerated its size or significance. These were all legitimate concerns, and they sparked a flurry of follow-up studies attempting to either confirm or refute the void's existence. What exactly is a cosmic void, and how do they form in the first place? To understand this, we need to go back to the very beginning of the universe. In the first few 100,000 years after the Big Bang, matter was distributed almost perfectly uniformly throughout space. I say almost because there were tiny fluctuations in density, variations of only about 1 part in 100,000. In some regions, there was very slightly more matter than average. In other regions, very slightly less. These microscopic variations were imprinted during the first fraction of a second of the universe's existence by quantum fluctuations that got stretched to cosmic scales during a period of exponential expansion called inflation. As the universe expanded and cooled, gravity began amplifying these tiny density differences. Regions that started out slightly denser than average had a bit more gravitational pull, which attracted nearby matter, which made them even denser, which increased their gravitational pull even more. It was a runaway process. Meanwhile, regions that started out slightly less dense than average lost matter to their denser neighbors, becoming increasingly underdense over time. After about 1 billion years, this process had created a distinctive pattern. The slight overdensities had collapsed into the first generation of galaxies, which began clustering together along filaments. The underdense regions, now thoroughly emptied of matter by gravitational attraction to the growing structure around them, had become voids. This pattern has been evolving ever since, with galaxies continuing to flow along filaments and fall into clusters while voids grow larger and emptier. The current consensus among cosmologists is that voids account for somewhere between 40 and 60% of the universe's total volume, depending on exactly how you define where a void ends and normal space begins. They're not exotic anomalies. They're a fundamental feature of how structure forms in an expanding universe governed by gravity. Most voids are relatively modest in size, measuring somewhere between 50 and 200 million light-years in diameter. These are often called typical voids, and they're found everywhere throughout the cosmic web. Then there are the supervoids, enormous bubbles of underdense space measuring 300 to 500 million light-years across. These are rarer, but still not particularly unusual. In the portions of the universe that have been mapped in detail, astronomers have identified dozens of supervoids. But the KBC void, if it really exists as a coherent structure, is in a different category entirely. At roughly 2 billion light-years in diameter, It's not just larger than a typical void or even a supervoid. It's approaching the scale of the largest structures that should theoretically be able to exist in the universe given its age and expansion history. This brings us to something called the cosmological principle, one of the foundational assumptions of modern cosmology. The principle states that on sufficiently large scales, the universe should be homogeneous and isotropic. That's fancy science talk for saying the universe should look basically the same in all directions and at all locations. There shouldn't be any special places or preferred directions. This principle is built into Einstein's equations of general relativity and forms the basis of the standard model of cosmology. But here's the problem. If we're inside an enormous void that's nearly 2 billion light-years across, are we violating the cosmological principle? Are we in a special location after all? The answer depends on what you mean by sufficiently large scales. Most cosmologists argue that you need to look at regions at least 300 to 500 million light-years across before the universe starts to look homogeneous. Below that scale, you expect to see structure like clusters, filaments, and voids. The KBC void, even at its largest extent, is only about 4 to 5 times larger than this homogeneity scale. That makes it unusual and statistically unlikely, but not necessarily impossible or in violation of any physical laws. Think of it this way. If you flip a coin 100 times, you expect to get about 50 heads and 50 tails. But occasionally, purely by chance, you might get 60 heads and 40 tails, or even 65 heads and 35 tails. These outcomes are unlikely but not impossible. They're just statistical fluctuations. The KBC void might be something similar, a rare statistical fluctuation in the distribution of matter, unlikely but not impossible. Except there's a problem with this analogy. The universe isn't infinite, and we can only observe a finite volume of space. If extremely large structures like the KBC void are genuinely rare, then finding ourselves inside one is suspicious. It's like flipping a coin 100 times, getting 65 heads, and then discovering that these were the only 100 coin flips that will ever be performed in the entire history of the universe. Suddenly, that unlikely outcome seems a lot more significant. This statistical argument has been at the heart of the debate over the void's existence and importance. Several papers published in the late 2010s attempted to calculate the probability that a random observer in the universe would find themselves inside a void as large as the KBC void. The estimates varied widely depending on the assumptions made, but most papers converged on probabilities somewhere between 1 in 10 and 1 in 100. Those aren't impossible odds by any means. If you gathered 100 cosmologists in a room, you'd expect at least one of them to be born on Christmas Day purely by chance. But they're uncomfortable odds for a field that prides itself on discovering universal laws that apply everywhere and everywhen. The discomfort only grew as astronomers realized that being inside a large void might actually explain some otherwise puzzling observations. Throughout the late 1990s and early 2000s, cosmologists were developing increasingly precise measurements of the universe's expansion rate, known as the Hubble constant. Different research groups using different methods were getting systematically different answers, and the discrepancy wasn't going away as observations improved. It was getting worse. By the 2010s, this had evolved from a minor puzzle into what cosmologists were calling the Hubble Tension, one of the most significant problems in fundamental physics. And in 2015, several research groups independently realized that being inside a large underdense region could potentially explain this discrepancy. If the expansion rate we measure locally is influenced by the fact that we're inside a void, then the value we calculate might not represent the true global expansion rate of the universe. The connection between voids and expansion rates has to do with a subtle effect in general relativity. In Einstein's theory, space itself is dynamic. It can expand, contract, or curve in response to the presence of matter and energy. The average expansion rate of the universe is determined by its overall matter and energy content. But locally, the expansion rate can differ from the average if you're in a region that's significantly more or less dense than typical. Inside an underdense region like a void, there's less matter pulling things together gravitationally. This means that galaxies inside the void experience slightly less gravitational deceleration than galaxies in a typical region of space. The result is that, relative to us, galaxies appear to be receding slightly faster than they would if we were in a location with average cosmic density. When we measure the Hubble constant by observing galaxies within our local cosmic neighborhood, we're potentially measuring an expansion rate that's been slightly inflated by our position inside a void. The effect is subtle, only a few percent, but a few percent is exactly the size of the discrepancy that cosmologists have been struggling to explain. To understand why this matters, we need to understand what the Hubble constant actually tells us. It's not just some abstract number that cosmologists like to argue about. It's directly related to fundamental questions about the universe's age, size, composition, and ultimate fate. Get the Hubble constant wrong, and your entire cosmic timeline gets thrown off. Your estimates for when the first stars formed, when galaxies assembled, when the Earth came into being, all of it depends on knowing the universe's expansion rate with precision. For decades, the accepted value for the Hubble constant hovered around 70 kilometers per second per megaparsec. That's science talk for saying that for every megaparsec of distance about 3.26 million light-years, a galaxy appears to be receding from us about 70 kilometers per second faster. So, a galaxy 10 megaparsecs away is receding at 700 kilometers per second. A galaxy 20 megaparsecs away at 1400 kilometers per second, and so on. This specific value implies that the universe is approximately 13.8 billion years old and will continue expanding forever, with the expansion rate gradually slowing down over time due to the gravitational attraction of all the matter in the universe, but never quite stopping. But here's where things got weird. As measurement techniques improved through the 2000s and 2010s, two different approaches to measuring the Hubble constant began giving systematically different answers. The first approach uses what are called standard candles, objects whose intrinsic brightness is known. Type Ia supernovae are the most famous example. These stellar explosions all reach approximately the same peak brightness, so by measuring how bright they appear from Earth, astronomers can calculate how far away they are. By also measuring their redshift, which tells you how fast they're receding, you can calculate the Hubble constant. Multiple research groups, including a team led by Nobel laureate Adam Rice, have used this technique to measure a Hubble constant of about 73 kilometers per second per megaparsec, with an uncertainty of only about 1 or 2%. The second approach uses observations of the cosmic microwave background, the faint afterglow of the Big Bang that fills all of space. This radiation was emitted when the universe was only 380,000 years old, and it contains a wealth of information about the universe's composition and expansion history, encoded in tiny temperature fluctuations across the sky. By analyzing these fluctuations, using Einstein's equations of general relativity and the standard model of cosmology, scientists can extrapolate forward to predict what the universe's current expansion rate should be. The European Space Agency's Planck satellite, which made the most precise measurements of the cosmic microwave background to date, calculated a Hubble constant of about 67 kilometers per second per megaparsec, with an uncertainty of less than 1%. 67 versus 73. That might not sound like a huge difference, but in precision cosmology, it's enormous. Both measurements are incredibly precise, with uncertainties that have been reduced to the point where the two values don't overlap, even when you account for measurement errors. It's not that one measurement is right and the other is wrong. They're both measuring something real. The question is why they're measuring different things. This is the Hubble tension, and it's been keeping cosmologists up at night for the better part of a decade. There are really only three possible explanations. First, there could be systematic errors in one or both measurement techniques that haven't been properly accounted for. Maybe type Ia supernovae aren't quite as standard as we think, or maybe there's some subtle effect in the cosmic microwave background data that's being misinterpreted. This is the most conservative explanation, but it's becoming increasingly difficult to maintain as both techniques have been refined and cross-checked in multiple ways. The second possibility is that there's new physics at play. Perhaps dark energy, the mysterious force causing the universe's expansion to accelerate, doesn't behave quite the way we think it does. Perhaps it's stronger now than it was in the early universe, which would cause the local expansion rate to be higher than predicted from cosmic microwave background observations. Or perhaps there are additional particles or forces that we haven't discovered yet that affect the universe's expansion history. This is the exciting possibility, because it would mean we're on the verge of a major revolution in fundamental physics. The third possibility, the one that's most relevant to our story, is that we're measuring a local expansion rate that differs from the global average because of our position inside the KBC void. This explanation has the advantage of not requiring any new physics or systematic errors. It just requires accepting that we live in a statistically unusual location. Several research papers published between 2015 and 2020 explored this possibility in detail. The basic idea is straightforward. If we're inside a large underdense region, then galaxies within that region are subject to an unusual gravitational environment. There's less matter pulling them back than there would be in a typical region of space. As a result, they're receding from us slightly faster than they would if we were in an average location. When we use nearby galaxies to measure the Hubble constant, we're potentially measuring this locally enhanced expansion rate rather than the true global rate. The models varied in their specifics, but most suggested that being inside a void with the size and density contrast of the KBC void could potentially boost the locally measured Hubble constant by somewhere between 3 and 7 kilometers per second per megaparsec. That's almost exactly the size of the discrepancy between local and cosmic microwave background measurements. The match seemed almost too good to be true. Of course, as with any proposed solution to a major scientific problem, there were skeptics. Many cosmologists pointed out that while the void hypothesis could potentially explain the Hubble tension, it raised as many questions as it answered. For one thing, the void would need to have very specific properties to produce exactly the right size effect. The density contrast couldn't be too large or too small, and its size couldn't be too big or too small. It had to be just right, which seemed suspiciously convenient. Furthermore, if we're inside a void, that should affect other cosmological observations besides just the Hubble constant. It should slightly alter the apparent brightness and distribution of distant supernovae, the clustering of galaxies at different distances, the properties of the cosmic microwave background in subtle ways. Some of these predictions matched observations, while others didn't quite line up. The evidence was intriguing but not conclusive. By 2020, the scientific literature contained a roughly equal number of papers arguing that the void hypothesis could explain the Hubble tension and papers arguing that it couldn't. The debate had reached a kind of stalemate, with both sides dug into their positions and waiting for new data to break the tie. That new data was supposed to come from next-generation galaxy surveys that would map the three-dimensional distribution of galaxies with unprecedented precision and to much greater distances than previous surveys. Projects like the Dark Energy Spectroscopic Instrument, or DSC, which began operations in 2021, and the European Space Agency's Euclid satellite, launched in 2023, promised to map tens of millions of galaxies out to distances of 10 billion light-years or more. With data of that quality, astronomers would be able to definitively determine whether the KBC void exists as a coherent large-scale structure, precisely measure its size and density profile, and test whether being inside it could really explain the Hubble tension. But even before this new data started arriving, the void hypothesis was running into another problem. Several careful reanalyses of existing galaxy survey data, published in 2020 and 2021, cast doubt on whether the KBC void even exists in the form originally claimed. These studies used more sophisticated statistical techniques and more complete data sets than the original 2013 paper. What they found was more ambiguous than the clear-cut underdensity that Keenan, Barger, and Cowie had identified. According to these newer analyses, yes, our local cosmic neighborhood does appear to be somewhat underdense compared to the average universe. But the underdensity is smaller than originally claimed, somewhere around 20 to 30% rather than 40 to 50%. And it's not clear that this underdensity forms a coherent spherical or ellipsoidal structure that can be called a single void. Instead, it might be a more complex, irregular region of below-average density that happens to extend in multiple directions from our location. Furthermore, some of these studies found that the underdensity doesn't extend out to 2 billion light-years as claimed. Instead, it seems to fade back toward average cosmic density at distances of around 700 million to 1 billion light-years. If true, this would make our local underdensity more like an unusually large supervoid rather than an extreme outlier. This is still statistically unusual, but much less dramatically so than a structure stretching 2 billion light-years. These more recent studies haven't killed the void hypothesis entirely, but they've definitely deflated some of the more dramatic claims. The current scientific consensus, if there is one, seems to be that we do live in a region of below-average cosmic density, that this underdensity extends at least several hundred million light-years in most directions, but that calling it one of the largest voids in the universe might be an overstatement. And whether this underdensity is large enough and severe enough to explain the Hubble tension remains an open question that will probably require another decade of observations to resolve. But here's what makes this whole story fascinating from a philosophical perspective. Even if the KBC void turns out to be smaller or less extreme than initially thought, the very fact that we had to seriously consider whether we live in an unusual location represents a dramatic shift in how we think about our place in the cosmos. For the past 500 years, ever since Copernicus argued that Earth wasn't at the center of the universe, one of the guiding principles of astronomy and cosmology has been that there's nothing special about our location. Earth isn't at the center. The Sun is just one star among hundreds of billions. The Milky Way is just one galaxy among hundreds of billions. And our location within the cosmic web should be typical, unremarkable, average in every way. This principle, sometimes called the Copernican principle or the principle of mediocrity, has been extraordinarily successful. It's guided cosmologists to make correct predictions about the large-scale structure and evolution of the universe. It's philosophically satisfying because it suggests that the laws of physics we discover here on Earth apply everywhere else in the universe. We're not special, which means what we learn is universal. But the void hypothesis forces us to at least consider the possibility that maybe, just maybe, we are in a slightly unusual location. Not special in some cosmic sense. Not chosen by the universe or singled out for any particular reason. Just statistically unlikely, like being born on Christmas Day or rolling a natural 20. And, if that's the case, it has profound implications for how we do cosmology, because it means that some of our most careful measurements might not represent universal constants, but rather local peculiarities. The Hubble constant should be one of the most straightforward numbers in all of cosmology. It's literally just the rate at which the universe is expanding right now, expressed as a velocity per unit distance. Yet somehow, this single number has become the source of what many physicists are calling the biggest crisis in modern cosmology. To understand why this matters so much, we need to understand what cosmologists actually mean when they talk about the universe expanding and how they go about measuring that expansion. The idea that the universe is expanding at all would have seemed absurd to scientists a century ago. In the early 1920s, the dominant view was that the universe was static and eternal. Sure, things moved around within it. Stars orbited, planets spun, but the overall size and structure of the cosmos was thought to be unchanging. This view was so deeply ingrained that when Albert Einstein developed his general theory of relativity in 1915 and found that his equations predicted a dynamic universe that would either expand or contract, he actually modified them by adding a term called the cosmological constant specifically to keep the universe static. Einstein later called this his greatest blunder, but at the time, it seemed like the obvious thing to do. The universe couldn't be expanding because, well, look around. Everything seemed pretty stable. Then came Edwin Hubble. Working at the Mount Wilson Observatory in California in the late 1920s, Hubble was measuring the distances and velocities of galaxies, or what were then called nebulae, because astronomers weren't yet sure they were separate galaxies at all. What he discovered was shocking. The farther away a galaxy was, the faster it appeared to be moving away from us. There was a direct linear relationship between distance and recession velocity. Hubble published his findings in 1929, and the implications were revolutionary. If distant galaxies are all moving away from us, and the farther away they are, the faster they're receding, then the universe itself must be expanding. Space itself is stretching, carrying galaxies along with it like raisins in an expanding loaf of bread. The initial value Hubble calculated for his constant was about 500 kilometers per second per megaparsec, which is roughly 7 times higher than modern measurements. This was due to errors in his distance measurements, specifically an incorrect calibration of the Cepheid variable stars he was using as standard candles. But the discovery itself was sound, and it completely revolutionized our understanding of the cosmos. Over the following decades, astronomers worked to refine the measurement of the Hubble constant, and the value slowly came down as distance measurement techniques improved. By the 1950s, it was around 250. By the 70s, around 100. By the 90s, it had settled in the range of 65 to 75, which is roughly where it stands today, except now that range has become a source of enormous controversy. The modern measurement techniques are so precise that we can distinguish between a value of 67 and a value of 73 with high confidence. Both of these values are supported by multiple independent observations using completely different methods, and therein lies the crisis. Let's start with the local measurements, the ones that give us the higher value of around 73. These measurements use what astronomers call the cosmic distance ladder, a series of overlapping measurement techniques that allow us to determine distances to increasingly remote objects. The first rung of this ladder involves measuring distances to nearby stars using parallax, the apparent shift in a star's position as Earth orbits the Sun. This technique works reliably out to distances of a few thousand light-years and provides a solid foundation for everything else. The second rung uses certain types of variable stars, particularly Cepheid variables, whose intrinsic brightness is related to how quickly they pulsate. By measuring a Cepheid's pulsation period, you can determine its true brightness, and by comparing that to how bright it appears from Earth, you can calculate its distance. This works out to distances of around 100 million light-years. The third rung uses Type Ia supernovae, stellar explosions that reach approximately the same peak brightness regardless of where they occur. These are so luminous that they can be seen from billions of light-years away, making them ideal for probing deep into cosmic history. By carefully climbing this distance ladder, starting with nearby parallax measurements, then using those to calibrate Cepheid distances, then using Cepheids to calibrate supernova distances, astronomers can measure the distances to galaxies hundreds of millions of light-years away with remarkable precision. And by combining these distance measurements with redshift measurements that tell you how fast those galaxies are receding, you can calculate the Hubble constant. This is exactly what Adam Rice and his team have been doing for the past 2 decades. Using observations from the Hubble Space Telescope, they've measured Cepheid variables in dozens of nearby galaxies and used those measurements to calibrate the brightness of Type Ia supernovae. Their most recent results, published in 2022, give a Hubble constant of 73.04 kilometers per second per megaparsec, with an uncertainty of only 1.04. That's an error bar of less than 1.5%, which is extraordinarily precise for a cosmological measurement. But there's another completely independent way to measure the Hubble constant, one that doesn't rely on the distance ladder at all. This method uses observations of the cosmic microwave background, that faint afterglow of the Big Bang that pervades all of space. The cosmic microwave background was emitted when the universe was only 380,000 years old, less than 1/100% of its current age. At that time, the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms, a process called recombination. Before recombination, the universe was filled with a hot plasma of charged particles that scattered photons in all directions, making the universe opaque to light. After recombination, photons could travel freely through space, and those photons have been traveling ever since, getting stretched to longer and longer wavelengths as the universe expands. Today, we detect them as microwave radiation with a temperature of about 2.7 degrees above absolute zero. But the cosmic microwave background isn't perfectly uniform. There are tiny temperature variations, typically only about 1 part in 100,000, that reflect density variations in the early universe. Regions that were slightly denser were also slightly hotter, and these temperature fluctuations got frozen into the cosmic microwave background at the moment of recombination. By mapping these temperature variations across the entire sky, satellites like NASA's Wilkinson Microwave Anisotropy Probe and the European Space Agency's Planck mission have created incredibly detailed maps of the infant universe. These maps contain a treasure trove of information about the universe's composition, geometry, and expansion history. The key insight is that the pattern of temperature fluctuations in the cosmic microwave background depends on several fundamental parameters, including the density of ordinary matter, the density of dark matter, the density of dark energy, and the universe's expansion rate at the time the cosmic microwave background was emitted. By analyzing the statistical properties of these fluctuations, specifically the sizes and amplitudes of hot and cold spots at different angular scales, cosmologists can determine all of these parameters with remarkable precision. It's like forensic astronomy. You're using evidence from the distant past to reconstruct the conditions that must have existed back then. But here's the crucial part. Once you know the universe's composition and expansion rate 380,000 years after the Big Bang, you can use Einstein's equations of general relativity to calculate how the universe should have evolved from then until now. You're essentially running the expansion forward through time, accounting for how gravity slows the expansion, how dark energy accelerates it, and how the relative importance of different components changes as the universe grows. At the end of this calculation, you get a prediction for what the universe's current expansion rate, the Hubble constant, should be. This is the method used by the Planck team, and their result, published in 2018, gives a Hubble constant of 67.4 kilometers per second per megaparsec, with an uncertainty of only 0.5. That's even more precise than the local measurements, with an error bar of less than 1%. 67.4 versus 73.04. The two values differ by about 8%, which might not sound like much, but both measurements are so precise that this discrepancy is statistically significant at more than 5 sigma. In particle physics, 5 sigma is the gold standard for claiming a discovery. It means there's less than a 1 in 3.5 million chance that the discrepancy is due to random statistical fluctuations. When two measurements disagree at the 5 sigma level, something is genuinely wrong. Either one of the measurements has a systematic error that hasn't been properly accounted for, or our theoretical understanding is incomplete. For the first few years after this discrepancy became apparent, most cosmologists assumed it was the former. Systematic errors are common in complex measurements, and the history of science is full of examples where apparently precise measurements turned out to be wrong due to subtle effects that weren't initially considered. But as both measurement techniques have been refined and cross-checked over the past decade, the discrepancy hasn't gone away. If anything, it's gotten worse. Multiple independent teams using different telescopes, different analysis techniques, and different samples of galaxies and supernovae keep getting values around 73. And multiple independent analyses of cosmic microwave background data, including data from different satellites, keep getting values around 67. It's not a fluke. It's not a mistake. It's a genuine tension that's forcing cosmologists to seriously consider that our standard model of cosmology might be incomplete or incorrect. The standard model of cosmology, often called lambda CDM, is based on a few key ingredients. Lambda represents dark energy, the mysterious force causing the universe's expansion to accelerate. CDM stands for cold dark matter, the invisible substance that makes up about 27% of the universe's total mass energy content. The remaining ingredients are ordinary matter, about 5%, and radiation, which is negligible in the present-day universe, but was important in the early universe. This model has been extraordinarily successful at explaining a vast range of observations. It correctly predicts the abundances of light elements like hydrogen, helium, and lithium that were forged in the first few minutes after the Big Bang. It explains the pattern of temperature fluctuations in the cosmic microwave background. It accounts for the large-scale distribution of galaxies and the properties of galaxy clusters. It matches observations of distant supernovae that revealed the universe's accelerating expansion. For the past 25 years, lambda CDM has been the consensus model of cosmology, tested and validated by countless observations. But the Hubble tension suggests that something in this picture is wrong, or at least incomplete. There are really only three categories of explanation. First, there could be systematic errors in the local distance ladder, measurements. Perhaps Cepheid variable stars don't all behave exactly the same way, or perhaps type Ia supernovae vary in their peak brightness in ways we haven't fully accounted for. Perhaps there's dust between us and the objects we're observing that's dimming their light and making them appear farther away than they really are. These possibilities have been exhaustively investigated by multiple research groups, and while systematic errors can never be completely ruled out, most experts believe they're unlikely to explain the full magnitude of the discrepancy. The measurements have been cross-checked using alternative distance indicators like red giant stars and the tip of the red giant branch method. Different teams have used different samples of galaxies in different regions of the sky. They've accounted for the effects of dust, metallicity variations, and dozens of other potential sources of error. And yet the value keeps coming out around 73. Second, there could be problems with the cosmic microwave background analysis, or with the assumptions that go into extrapolating from conditions in the early universe to the present day. Perhaps the universe's expansion history is more complex than we think, with the expansion rate varying in unexpected ways over cosmic time. Perhaps there are subtle features in the cosmic microwave background data that are being misinterpreted. Perhaps general relativity doesn't quite work the same way on cosmological scales as we think it does. Again, these possibilities have been carefully studied, and most experts believe they're unlikely to fully resolve the tension. The cosmic microwave background measurements have been validated using data from multiple satellites and multiple analysis pipelines. The statistical methods are robust, and the results are consistent across different approaches. The third category of explanation is new physics. Perhaps there's something about the universe's composition or behavior that we simply don't know yet. This is both the most exciting and the most troubling possibility. Exciting because discovering new physics is how science makes its greatest leaps forward. Troubling because it would mean that lambda CDM, which has worked so well for so long, needs to be modified or replaced. There's no shortage of proposed new physics that could potentially resolve the Hubble tension. Some models suggest that dark energy might not be constant, but instead varies with time, being stronger in the present-day universe than it was in the past. This would cause the local expansion rate to be higher than predicted from early universe observations. Other models propose the existence of additional types of particles or fields that affect the universe's expansion history in subtle ways. One particularly intriguing idea involves what are called early dark energy models, which propose that dark energy was briefly important in the very early universe, well before the cosmic microwave background was emitted. This would affect the expansion rate at early times in a way that would propagate forward to affect the relationship between early and late-time measurements of the Hubble constant. Still, other models suggest modifications to general relativity itself, proposing that gravity works slightly differently on the largest cosmic scales than Einstein predicted. These are radical ideas, and they come with their own problems and complications. Most proposed modifications to lambda CDM solve the Hubble tension, but create other tensions with different observations. It's like fixing a leak in your roof only to discover that the patch has caused a new leak somewhere else. This is where the void hypothesis enters the picture, because it offers a potential explanation for the Hubble tension that doesn't require any new physics at all. The idea is deceptively simple. What if both measurements are correct, but they're measuring different things? What if the local measurements are giving us the expansion rate within our local void, while the cosmic microwave background is giving us the global average expansion rate of the universe? To understand how this could work, we need to understand a subtle point about how the universe expands. In the standard cosmological model, space expands uniformly everywhere. Every region of space is stretching at the same rate, described by a single universal expansion rate, the Hubble constant. But this is an idealization that ignores the effects of local density variations. In reality, the expansion rate can vary slightly from place to place depending on the local matter density. In a dense region, like a galaxy cluster, gravity is strong enough to overcome the cosmic expansion entirely. Galaxies within a cluster are gravitationally bound to each other and don't participate in the Hubble expansion at all. In fact, they're often moving toward each other, and cluster galaxies regularly collide and merge. On slightly larger scales, in regions that are denser than average but not quite dense enough to form gravitationally bound structures, the expansion is happening but at a slower rate than the cosmic average. The extra matter in these regions exerts additional gravitational pull that partially counteracts the expansion. Conversely, in underdense regions like voids, there's less matter pulling back against the expansion. Galaxies in these regions experience less gravitational deceleration, which means they're receding from each other slightly faster than they would in a region of average density. The expansion rate in a void is slightly higher than the cosmic average. This effect is predicted by general relativity and has been known since the equations describing the expansion of an inhomogeneous universe were first worked out in the 1970s and 80s. But for most purposes, cosmologists have ignored it because the variations in expansion rate due to local density fluctuations are typically very small, only 1% or 2% at most. That's smaller than the measurement uncertainties in most cosmological observations, so it can usually be safely neglected. However, if we're inside an unusually large and underdense void, and if we're using galaxies within that void to measure the Hubble constant, then we might be systematically overestimating the true global expansion rate of the universe. The locally measured value could be boosted by several percent compared to what observers in a typical location would measure, which is roughly the size of the discrepancy we're trying to explain. Several research groups have developed detailed models of how being in a void would affect Hubble constant measurements. The models vary in their specifics, but they all share the same basic structure. You start with a model of the cosmic web that includes both dense regions and voids. You place an observer inside a void and calculate what that observer would measure when looking at galaxies at various distances. The key insight is that the effect depends on distance. For very nearby galaxies, the ones right next to us in the void, the enhanced local expansion rate dominates. These galaxies appear to be receding faster than they would if we were in an average location. But as you look at galaxies farther and farther away, eventually you're looking beyond the edge of the void into regions of more typical density. At these larger distances, the expansion rate returns to the cosmic average. The result is that measurements of the Hubble constant using relatively nearby galaxies, those within a few hundred million light-years, can give systematically higher values than the true global average, with the size of the bias depending on the size and density contrast of the void. For the void hypothesis to explain the Hubble tension, our local void would need to have fairly specific properties. The density deficit would need to be large enough to produce a several % effect on the expansion rate, but not so large that it would be glaringly obvious in other observations. The void would need to extend out to at least a few hundred million light-years, far enough to encompass most of the galaxies used in local Hubble constant measurements, but not so far that it would dramatically affect observations at even greater distances. And the transition from underdense to average density at the edge of the void would need to be relatively gradual rather than sharp, because a sharp boundary would produce observable effects that haven't been seen. When the first detailed void models were published around 2017, many cosmologists were intrigued. The required void properties were unusual but not impossible. They were roughly consistent with what had been claimed for the KBC void, though with some important caveats. If the void was real and had the right properties, it could potentially explain the Hubble tension without requiring any modifications to fundamental physics. This was an attractive possibility, because it's generally preferable to exhaust conventional explanations before invoking new physics. But the void hypothesis came with its own problems, and these problems have become increasingly apparent as the idea has been scrutinized over the past several years. The first problem is statistical. As mentioned earlier, a void as large as the KBC void would be quite rare. If we calculated the probability that a random observer would find themselves inside such a structure, the odds are somewhere between 1 in 10 and 1 in 100, depending on exactly how you do the calculation. That's not impossibly unlikely, but it does raise an uncomfortable question. Why should we be so lucky or unlucky as to find ourselves in such an unusual location? This brings us to something called the Copernican principle, which I mentioned briefly earlier, but which deserves a more thorough examination because it's at the philosophical heart of this entire debate. The principle is named after Nicolaus Copernicus, the 16th century astronomer who proposed that Earth orbits the Sun rather than the other way around. This was a radical idea at the time because it dethroned Earth from its position at the center of the universe. Before Copernicus, the dominant cosmological model, inherited from ancient Greek philosophers and enshrined in Christian theology, placed Earth at the center of everything with the Sun, Moon, planets, and stars all revolving around us. This geocentric model wasn't just astronomy. It was a statement about humanity's special place in the cosmic order. Copernicus's heliocentric model fundamentally challenged this worldview by suggesting that Earth was just another planet, no more central or special than Venus or Mars. This shift from geocentrism to heliocentrism was the first step in what has been called the demotion of humanity from cosmic significance. Over the following centuries, we discovered that the Sun isn't at the center of the universe either. It's just one star among hundreds of billions in the Milky Way galaxy, and it's not even in a particularly special location within the galaxy. We're out in the suburbs, about 2/3 of the way from the center to the edge, in a rather ordinary spiral arm. Then we discovered that the Milky Way isn't the only galaxy. It's just one among hundreds of billions of galaxies scattered throughout the observable universe, and it's not a particularly large or impressive one. We're not in a giant elliptical galaxy or at the center of a massive galaxy cluster. We're in a fairly ordinary spiral galaxy that's part of a fairly ordinary small group of galaxies called the local group. At each stage of this process, we've learned that we're less special and more typical than we previously thought. This pattern has been so consistent that it's been elevated to a principle. The Copernican principle, also called the principle of mediocrity, states that we should assume we're typical observers in typical locations unless we have strong evidence to the contrary. This principle has been extraordinarily useful in cosmology. It's what allows us to take observations made from our specific location in space and time, and extrapolate them to make statements about the universe as a whole. If we assumed we were in a special location, then our observations might not tell us much about the typical properties of the cosmos. But if we assume we're typical, then what we see around us should be representative of what exists everywhere else. The Copernican principle is built into the foundations of modern cosmology through what's called the cosmological principle, which states that on sufficiently large scales, the universe is homogeneous and isotropic. Homogeneous means it looks the same at every location, and isotropic means it looks the same in every direction. This principle is not derived from any fundamental physical laws. It's an assumption based on the Copernican idea that there are no special places in the universe. And for the most part, observations have validated this assumption. The cosmic microwave background looks almost perfectly uniform in all directions, with temperature variations of only 1 part in 100,000. The distribution of galaxies, when averaged over sufficiently large volumes, is roughly the same everywhere we look. The laws of physics appear to work the same way in distant galaxies as they do in laboratories on Earth. But the void hypothesis, if true, would represent a significant deviation from the Copernican principle. Not a complete violation, but certainly a stretching of the idea that we're in a typical location. If we're inside one of the largest voids in the observable universe, a structure whose size places it in the tail of the statistical distribution, then we're not typical by definition. We're unusual, not in some mystical or teleological sense, but simply as a matter of statistical rarity. This doesn't mean the void hypothesis is wrong. Statistical outliers exist, and somebody has to be in them. But it does raise the question of why we should invoke such an explanation unless we've exhausted all other possibilities. This is one reason why many cosmologists have been reluctant to embrace the void hypothesis, even as the Hubble tension has persisted and deepened. There's a general preference in science for explanations that don't require special circumstances or unlikely coincidences. The second major problem with the void hypothesis is empirical. If we're inside a large void, that should affect more than just the locally measured Hubble constant. It should leave its fingerprints on a variety of other cosmological observations, and when you look carefully, some of those fingerprints are missing or inconsistent. For example, being in a void should affect the apparent distribution of galaxies at different distances. As you look out from the center of a void toward its edges, you should see the density of galaxies gradually increasing. Several studies have looked for this signature in galaxy survey data, and the results have been mixed. Some studies claim to see the expected pattern, while others don't. One particularly important test involves something called the kinetic Sunyaev-Zeldovich effect, which is a subtle distortion in the cosmic microwave background caused by the motion of galaxy clusters. If we're inside a large void, the matter distribution in our local neighborhood is different from the cosmic average, and this should affect the large-scale flows of matter in characteristic ways that would show up in measurements of the kinetic Sunyaev-Zeldovich effect. Several research groups have looked for this signature, and again, the results have been inconclusive. Some studies claim to see evidence consistent with a local void, while others see no significant effect. Part of the problem is that these measurements are very difficult. The signals are weak, the data is noisy, and there are many potential sources of systematic error. But the lack of clear, unambiguous confirmation of the void's effects on multiple independent observations has made many cosmologists skeptical that a void large enough to explain the Hubble tension really exists. The third problem is theoretical. Even if a void of the right size and density contrast exists, it's not entirely clear that it would produce exactly the right size effect to explain the Hubble tension. The calculations involved are complex because you need to properly account for how light travels through an inhomogeneous universe, how the expansion rate varies with position and distance, and how observers would actually measure the Hubble constant in practice. Different research groups using different modeling approaches have gotten different answers for how large an effect a given void would produce. Some models suggest that even a void as large as the KBC void would only change the locally measured Hubble constant by 2 or 3 kilometers per second per megaparsec, which is not quite enough to explain the full discrepancy. Other models suggest it could produce an effect of 4 to 6, which would be sufficient. The discrepancy between models comes down to technical details about how the calculations are performed, which assumptions are made, and how various second-order effects are treated. This kind of disagreement between theoretical calculations is not uncommon in cosmology, but it does mean that the void hypothesis is not as straightforward as it might initially appear. By the early 2020s, after several years of intense study, the scientific community had reached a kind of uneasy stalemate regarding the void hypothesis. On one hand, it remained a viable potential explanation for the Hubble tension, one that didn't require any exotic new physics and was broadly consistent with some observations. On the other hand, the evidence for a void large enough and dense enough to fully explain the tension was not conclusive, and alternative explanations involving new physics or systematic errors in measurements remained on the table. What was needed to break this stalemate was better data, and fortunately, better data was on the way. Several next-generation astronomical surveys designed to map the three-dimensional distribution of galaxies with unprecedented precision began operations in the early 2020s. The most ambitious of these was the Dark Energy Spectroscopic Instrument, or DSI, which mounted on a telescope in Arizona began systematically measuring the red shifts of tens of millions of galaxies starting in 2021. DSI's goal was to create the most detailed three-dimensional map of the universe ever made, reaching out to distances of 10 billion light-years or more. With data of this quality, astronomers would be able to map the cosmic web in exquisite detail, identifying every significant void, filament, and cluster within billions of light-years of Earth. If the KBC void exists as claimed, DSI would see it clearly. If it doesn't exist or is smaller than claimed, that would also become apparent. In parallel, the European Space Agency launched the Euclid Space Telescope in July 2023. Euclid's mission is complementary to DESI's. While DSE measures galaxy redshifts from the ground, Euclid images galaxies from space with superb resolution and measures their shapes and positions. Together, these two surveys are providing cosmologists with an unprecedented view of the large-scale structure of the universe. The first results from DSI were published in early 2024, and they were intriguing but not definitive regarding the void question. DSI confirmed that our local cosmic neighborhood, out to distances of about 500 million light-years, does appear to be somewhat underdense compared to the average universe. The density deficit is real, though perhaps not quite as severe as the original KBC void papers claimed. But DESI also showed that the structure of this underdense region is more complex than a simple spherical or ellipsoidal void. There are filaments and smaller dense regions embedded within the larger scale underdensity, giving the whole structure a more irregular, patchy character. This doesn't rule out the void hypothesis, but it complicates the picture. If we're inside a complex, irregularly shaped underdense region rather than a clean, well-defined void, then calculating the effect on the Hubble constant becomes even more challenging. Different lines of sight pass through different density environments, and the overall effect on the locally measured expansion rate could be quite different from what simple spherical void models predict. Furthermore, DSI's data suggested that beyond about 700 million light-years, the cosmic density returns to something close to the universal average. There's not strong evidence for a huge underdense region extending out to 2 billion light-years as some versions of the KBC void hypothesis required. This is more consistent with the picture of an unusually large supervoid rather than an extreme outlier that would be one of the largest structures in the observable universe. As of early 2025, when DSE and Euclid continue releasing new results, the scientific consensus seems to be shifting toward a more nuanced view. Yes, we're in a region of below-average density. No, it's probably not large enough or extreme enough to fully explain the Hubble tension on its own. But it might still contribute 1% or 2% to the locally measured expansion rate, which could be part of the explanation even if it's not the whole story. This leaves cosmologists in a somewhat uncomfortable position. The Hubble tension remains unresolved. Local measurements continue to give values around 73, while cosmic microwave background predictions continue to give values around 67. The void hypothesis can perhaps explain part of this discrepancy, maybe 1 or 2 kilometers per second per megaparsec, but not all of it. So something else must be going on as well. Perhaps there are subtle systematic errors in the local distance ladder that haven't been fully accounted for. Perhaps there's some new physics that affects the universe's expansion history in ways we don't yet understand. Perhaps it's some combination of both. The frustrating reality is that despite years of intensive research involving some of the best minds in cosmology, we still don't have a clear answer. The Hubble tension persists, and it's not going away. If anything, as measurements have become more precise, the tension has only gotten worse. This has led some physicists to describe the current situation as a crisis in cosmology. That might sound melodramatic, but it's not entirely hyperbole. The Hubble constant is one of the most fundamental parameters describing our universe. It's directly related to the universe's age, size, and ultimate fate. If we can't measure it consistently, if different methods give systematically different answers, then something fundamental about our understanding of cosmology is wrong. The stakes are high because resolving the Hubble tension likely requires either discovering new physics or dramatically revising our picture of cosmic structure, or both. Either outcome would represent a major revolution in our understanding of the universe. And revolutions in physics, while exciting, are also deeply unsettling, because they force us to abandon ideas we thought were solidly established. For now, the mystery endures, and the void hypothesis remains one piece of a very complex puzzle. Whether we're inside a cosmic hole that's affecting our measurements, or whether the answer lies elsewhere, will likely become clearer over the next several years as data from DESI, Euclid, and other surveys continues to accumulate. But one thing is certain. The universe has surprised us before, and it will almost certainly surprise us again. The question is whether the next surprise will be that we're in a more unusual location than we thought, or that the laws governing cosmic expansion are more complex than we imagined. The history of science is littered with moments when humans discovered they weren't as special as they thought they were. Each discovery pushed us further from the center of things, further from cosmic significance, until we arrived at our current position as inhabitants of an ordinary planet orbiting an ordinary star in an ordinary galaxy in an ordinary part of the universe. Or at least, that's the story we've been telling ourselves for the past few centuries. But what if that story is wrong? Not completely wrong, but wrong in a subtle and important way. What if we actually are in a slightly unusual location after all? The possibility that Earth sits inside one of the largest voids in the observable universe forces us to confront an uncomfortable question that goes to the very heart of how we do science. Are we typical observers in a typical location, or are we statistical outliers who just happen to find ourselves somewhere unusual? And if we are outliers, does that change how we should interpret our observations of the cosmos? These aren't just abstract philosophical questions. They have profound practical implications for cosmology, because the entire enterprise of understanding the universe is based on the assumption that what we see from our particular vantage point is representative of what exists everywhere else. If that assumption is wrong, then some of our most cherished conclusions about the universe might need to be revised. Let's start by quantifying just how unusual it would be to find ourselves inside a structure like the KBC void. To do this, cosmologists use large computer simulations of cosmic structure formation. These simulations start with conditions similar to those in the very early universe, with tiny density fluctuations distributed randomly throughout space, and then evolve those fluctuations forward through billions of years of cosmic time using the known laws of physics. Gravity amplifies the initial fluctuations, causing overdense regions to collapse into galaxies and clusters, while underdense regions expand into voids. The result is a synthetic universe, a computer-generated cosmos that should statistically resemble the real universe if our theoretical understanding is correct. By analyzing the structure that forms in these simulations, cosmologists can determine how common voids of different sizes are. The results show that small voids, those measuring 50 to 100 million light-years across, are extremely common. Nearly every randomly placed observer in the simulated universe would find at least one such void within a few 100 million light-years of their location. Medium-sized voids, those in the 100 to 300 million light-year range, are less common but still not particularly rare. You'd expect a typical observer to have several within their observable neighborhood. But large voids, those exceeding 500 million light-years in diameter, are genuinely rare. Only about 5 to 10% of randomly placed observers would find themselves within such a structure. and superlarge voids approaching 1 billion light-years or more. Those are extreme outliers, appearing in only 1 or 2% of locations. Now, where exactly does the KBC void fall on this spectrum? That depends on whose analysis you believe. The original papers from the mid-2010s claimed a void extending out to nearly 2 billion light-years, which would place it firmly in the extreme outlier category. If that were correct, the probability of a random observer finding themselves inside such a structure would be somewhere around 1 in 100 or even lower. More recent analyses suggest something more modest, perhaps a void extending 700 million to 1 billion light-years, with a density deficit of about 20 to 30%. This would still be unusual, placing it in the top few percent of void sizes, but not quite as extreme. The probability of finding yourself in such a location would be more like 1 in 20 to 1 in 50. These aren't impossible odds by any means, but they're uncomfortable. They're the kind of odds that make scientists nervous because science is supposed to discover universal laws, not special cases. The discomfort comes from a principle that has been central to physics and astronomy for centuries. We assume that the laws of nature are the same everywhere, and that we occupy no special position from which to observe them. This assumption has been spectacularly successful. It's what allowed Newton to realize that the same gravitational force pulling an apple to the ground also keeps the moon in orbit around Earth and the planets in orbit around the sun. It's what allowed Einstein to develop general relativity by assuming that the laws of physics should look the same to all observers, regardless of their motion or location. It's what allowed Hubble to take observations of a few dozen nearby galaxies and extrapolate them into a universal expansion law. But here's the subtle point that often gets lost in discussions of the Copernican principle. The principle doesn't say that every location in the universe must be identical. That would be obviously false. We can see with our own eyes that some regions of space are dense with galaxies, while others are nearly empty. What the principle actually says is that we shouldn't assume we're in a special location without good reason. In other words, if there are many different types of locations in the universe, some common and some rare, we should expect to find ourselves in one of the common types unless we have specific evidence pointing otherwise. This is ultimately a statistical argument. If 95% of observers live in regions of average cosmic density and only 5% live in large voids, then you'd expect to be in the first group rather than the second. Finding yourself in the second group wouldn't violate any laws of physics, but it would be surprising. It would be like rolling a 20-sided die and getting a 20. Possible, but unlikely. The question is whether being surprised is sufficient reason to reject an explanation. In everyday life, unlikely things happen all the time. Someone wins the lottery despite odds of millions to 1 against. Someone is born on February 29th. Someone survives a plane crash. These events are individually unlikely, but collectively inevitable given enough opportunities. With about 8 billion people currently alive on Earth, even 1 in a billion events should happen about 8 times. The universe, or at least the observable universe, contains an enormous number of potential observer locations. There are at least 100 billion galaxies, each containing billions of stars, many of which likely have planets. If even a tiny fraction of those planets develop intelligent life, there could be millions or billions of observer locations scattered throughout the cosmos. Given that many opportunities, someone has to be in the rare locations. The question is whether that someone is us. This brings us into territory that makes many scientists deeply uncomfortable because it starts to sound like anthropic reasoning. The anthropic principle, in its weakest form, simply states that our observations of the universe are necessarily biased by the fact that we exist to make those observations. We shouldn't be surprised to find ourselves on a planet with liquid water and oxygen, for instance, because those conditions were presumably necessary for our kind of life to evolve. We couldn't have evolved on a planet without those conditions, so of course we find ourselves on one that has them. This weak version of the anthropic principle is relatively uncontroversial. It's just a reminder to account for selection effects when interpreting observations. But there's also a stronger version of the anthropic principle that makes much bolder claims. It suggests that the fundamental constants of nature, things like the strength of gravity, the mass of the electron, the speed of light, are fine-tuned to values that allow for the existence of complex structures like stars, planets, and living organisms. Change any of these constants by even a small amount, the argument goes, and the universe would be sterile and lifeless. The strong anthropic principle attempts to explain this apparent fine-tuning by invoking the multiverse. The idea that our universe is just one of countless universes with different physical constants. In most of those universes, the constants don't allow for life, so there's no one around to observe them. We necessarily find ourselves in one of the rare universes where the constants are just right, because those are the only universes that contain observers. Whether you find this argument convincing or meaningless depends largely on your philosophical inclinations, but most physicists are deeply skeptical of strong anthropic reasoning. The problem is that it's unfalsifiable. If you can explain any observation by saying we must observe it this way because otherwise we wouldn't exist to make the observation, then you're not really explaining anything. You're just restating the observation in different words. This is why most cosmologists are reluctant to invoke anthropic arguments unless absolutely necessary. But the void hypothesis brings us uncomfortably close to anthropic territory, because it raises the question of whether void environments might be preferential for the emergence of intelligent life. If so, then finding ourselves in a large void wouldn't be surprising at all. It would be exactly what we should expect, even if such voids are statistically rare, because most observers would be in voids rather than in typical regions of space. Is there any reason to think that voids might be better environments for life? At first glance, this seems backwards. Voids have fewer galaxies, which means fewer stars, which means fewer planets, which should mean fewer opportunities for life to arise. All else being equal, you'd expect dense regions with lots of galaxies to be more favorable for life simply because there are more places for it to develop. But all else might not be equal. One of the most significant hazards facing life in the universe is radiation. High-energy particles and photons can damage biological molecules, cause mutations, and, in extreme cases, completely sterilize planetary surfaces. Most of this dangerous radiation comes from astrophysical sources like supernovae, gamma-ray bursts, active galactic nuclei, and quasars. In dense regions of the universe, particularly in galaxy clusters, these violent events are more common simply because there are more galaxies packed into a smaller volume. A planet in a galaxy cluster might be bombarded by radiation from its neighbors far more frequently than a planet in an isolated galaxy in a void. There's some evidence that galaxies in clusters experience higher rates of supernovae and other energetic events due to interactions between galaxies. When galaxies pass close to each other or collide, the gravitational disruption can trigger bursts of star formation. and more star formation eventually leads to more stellar deaths, including supernovae. Furthermore, many galaxy clusters contain active galactic nuclei at their centers, supermassive black holes that are actively feeding and producing enormous amounts of radiation. A planet unlucky enough to be in a galaxy near one of these active nuclei could be bathed in dangerous X-rays and gamma rays. By contrast, galaxies in voids are typically more isolated. They interact with their neighbors less frequently, experience lower rates of dynamically triggered star formation, and are farther from sources of high-energy radiation. This doesn't mean they're completely safe. Individual galaxies still produce supernovae, and a sufficiently close supernova could certainly threaten any nearby planets. But the overall radiation environment might be calmer and more stable, which could be favorable for life. Another factor to consider is the availability of heavy elements. Life as we know it requires elements heavier than hydrogen and helium, particularly carbon, nitrogen, oxygen, and phosphorus. These elements are forged inside stars and distributed into space when stars die. In the early universe, heavy elements were scarce, and it took billions of years of stellar processing to enrich the interstellar medium to levels that could support rocky planets and potentially life. Galaxies in dense environments tend to be older and more evolved. They've had more time to process gas through multiple generations of stars, building up higher concentrations of heavy elements. This might seem like an advantage for life, but there's a complicating factor. In very dense environments, galaxies can have their gas stripped away by interactions with hot intracluster gas or by tidal effects from neighboring galaxies. Once a galaxy loses its gas, it can no longer form new stars, and without new star formation, it becomes a dead galaxy composed only of old stars slowly fading away. This process, called galaxy quenching, is common in clusters but rare in voids. Galaxies in voids tend to retain their gas for longer and continue forming stars at a steady rate for many billions of years. This means they might have a longer window of opportunity during which habitable planets can form and life can develop. The optimal environment for life might be somewhere in between the extremes. Not in a dense cluster where radiation hazards are high and galaxies get quenched, but not in a completely isolated void where heavy element enrichment proceeds slowly. Perhaps galaxies in large voids, which have some neighbors but not too many, represent a sweet spot. They're isolated enough to avoid the worst radiation hazards and to continue forming stars, but connected enough to have undergone sufficient chemical enrichment. This is all highly speculative, of course. We have exactly one example of life in the universe, the life on Earth, and we have no idea how representative or unusual the conditions that gave rise to it might be. But if void environments do turn out to be preferential for life, even slightly, then the fact that we find ourselves in a large void suddenly becomes much less surprising. It would be an example of what's called observer selection bias. The universe might be mostly empty of observers, with most of them clustered in particular types of environments, and we'd necessarily find ourselves in one of those environments, even if they're statistically rare. The problem with this reasoning is the same problem that plagues all anthropic arguments. It's very difficult to test. We can't survey the universe to count how many intelligent civilizations exist and where they're located. We have no way to determine whether voids really are preferential for life, or whether we're just engaging in motivated reasoning to explain away an uncomfortable coincidence. This is why most cosmologists prefer to avoid anthropic explanations, unless all other options have been exhausted. And in the case of the Hubble tension and the void hypothesis, other options definitely haven't been exhausted. There could still be systematic errors in measurements. There could be new physics we haven't discovered. The void might be smaller or less significant than claimed. Any of these explanations would be preferable to invoking selection bias because they'd be testable and falsifiable. But the anthropic question lurks in the background, impossible to completely dismiss. If we do turn out to be in a genuinely unusual location, and if conventional explanations prove inadequate, we might have no choice but to confront the possibility that our location isn't random. There's another aspect to the question of whether we occupy a special location that's worth considering, and it has to do with the observable universe itself. When we look out into space, we're looking back in time. Light travels at a finite speed, about 300,000 kilometers per second, which means that when we observe a distant galaxy, we're seeing it not as it is now, but as it was when the light left it millions or billions of years ago. The farthest objects we can observe are about 13.8 billion light-years away, which is the distance light could have traveled since the Big Bang. This defines the observable universe, a sphere centered on Earth with a radius of about 46.5 billion light-years. Wait, if the universe is 13.8 billion years old and light travels at a fixed speed, shouldn't the observable universe only be 13.8 billion light-years across? The answer has to do with the expansion of space. The objects that emitted the light we're receiving now were much closer to us when they emitted that light. But in the billions of years it took the light to reach us, space has been expanding, carrying those objects farther away. When you account for this expansion, the most distant observable objects are now about 46.5 billion light-years away, even though the light has only been traveling for 13.8 billion years. The crucial point is that the observable universe is centered on us. It's the region of space from which light has had time to reach Earth since the Big Bang. An observer in a different galaxy would have a different observable universe, a different sphere of space from which they could receive light. Most of their observable universe would overlap with ours, but the most distant regions would be different. They could see things we can't, and vice versa. Now, here's the interesting part. The observable universe is much smaller than the entire universe. We don't know how much smaller because we don't know how large the whole universe is. It could be just slightly larger than the observable region, or it could be infinite. Current observations are consistent with an infinite universe, but they can't prove it. The curvature of space, which would tell us whether the universe is finite or infinite, is too close to flat for us to measure definitively. If the universe is much larger than the observable region, and if cosmic structure continues beyond what we can see, then the portion we can observe might not be representative of the whole. Just as a small sample isn't always representative of a large population, the observable universe might not be representative of the entire universe. This is where the cosmological principle becomes not just a philosophical stance, but a practical necessity. If we can't assume that the observable universe is representative, then we can't extrapolate from our observations to make statements about the universe as a whole. We'd be stuck describing only what we can see, with no way to know whether it applies more broadly. For this reason, cosmologists generally assume that the universe beyond the observable region looks statistically similar to what we can see. There are no giant voids or supervoids that dwarf anything in our observable volume. There are no regions where the laws of physics work differently. Everything out there looks more or less like everything in here. But this is an assumption, not a proven fact, and it's worth remembering that it's an assumption made for practical rather than fundamental reasons. There's no law of physics that requires the universe to be homogeneous beyond our observational horizon. It's just convenient to assume it is. The void hypothesis doesn't challenge this assumption directly, but it does add an uncomfortable wrinkle. If we're inside a void that's a significant fraction of the size of the observable universe, then a substantial portion of what we can see might not be representative of the typical cosmic environment. We'd be looking at a biased sample, skewed toward the properties of underdense regions. This would be problematic for cosmology, because many of our conclusions about the universe's properties are based on observations that assume we're sampling typical conditions. For instance, measurements of the cosmic expansion rate using nearby galaxies assume that those galaxies are participating in the average cosmic expansion. If they're actually in a void and experiencing enhanced expansion, then our measurements are biased. Similarly, studies of galaxy evolution that use nearby galaxies as templates assume those galaxies are representative of galaxies in general. If void galaxies evolve differently from galaxies in typical environments, then our understanding of galaxy formation might be skewed. The good news is that we do observe galaxies and cosmic structure at many different distances, including distances far beyond any plausible void we might be inside. The cosmic microwave background, for instance, comes from a distance of about 45 billion light-years, almost at the edge of the observable universe. No void, not even the most extreme version of the KBC void, extends anywhere close to that far. This gives us a way to check whether our local observations are representative. By comparing the properties of nearby structure with the properties of distant structure, we can test for systematic differences that might indicate local peculiarities. So far, these comparisons have generally supported the idea that the universe is relatively homogeneous on large scales. Yes, there are voids and filaments and clusters, but when you average over sufficiently large volumes, the density and properties of cosmic structure are roughly the same everywhere. This is reassuring, but it doesn't completely eliminate the concern that our local neighborhood might be somewhat unusual. The question isn't whether the universe is generally homogeneous, it clearly is, but whether we happen to be in a location that deviates from the average by enough to affect certain precision measurements. And that question remains open. There's yet another angle to consider when thinking about whether we occupy a special location, and it has to do with other cosmic anomalies that have been discovered in recent decades. The KBC void isn't the only large-scale structure that's raised eyebrows among cosmologists. There are several other features of the observable universe that seem somewhat unusual or unexpected, and some researchers have speculated that they might all be connected. One of the most famous anomalies is the CMB cold spot, a region of the cosmic microwave background that's significantly colder than surrounding areas. The cold spot is about 5 degrees across on the sky, which is quite large, and it's about 70 microkelvins colder than the average temperature of the cosmic microwave background. That might not sound like much, but the typical temperaure fluctuations in the cosmic microwave background are only about 18 microkelvins, so the cold spot stands out as an outlier. When the cold spot was first clearly identified in data from the Wilkinson Microwave Anisotropy probe in 2004, some researchers suggested it might be a statistical fluke, the kind of thing that could happen by chance if you look at enough data. The cosmic microwave background covers the entire sky, and if you stare at random fluctuations long enough, you're bound to find some that look unusual. but subsequent analysis suggested that the cold spot was more anomalous than you'd expect from random fluctuations. The probability of such a feature appearing by chance was calculated to be somewhere between 1 in 50 and 1 in a few thousand, depending on exactly how you defined the anomaly. One proposed explanation for the cold spot is that it's caused by a supervoid along the line of sight. If there's an enormous underdense region between us and the cosmic microwave background in that particular direction, photons from the cosmic microwave background would experience a phenomenon called the integrated Sachs-Wolf effect. This is a subtle effect where photons gain or lose energy depending on the gravitational environment they travel through. Photons climbing out of a gravitational potential will lose energy and get redshifted, while photons falling into a potential will gain energy and get blue-shifted. In a static universe, these effects would exactly cancel as the photon enters and exits the potential well. But in an expanding universe, the potential well becomes shallower as the universe expands, which means the photon doesn't gain back all the energy it lost. The net result is a small redshift, which shows up as a cold spot in the cosmic microwave background. Several research groups have searched for evidence of a supervoid in the direction of the CMB cold spot, and some claim to have found it. A structure known as the Eridanus supervoid, located about 3 billion light-years away in the direction of the cold spot, has been proposed as a potential explanation. However, other studies have questioned whether this supervoid is large enough and underdense enough to fully explain the cold spot, and the debate continues. What's interesting for our purposes is that both the KBC void and the Eridanus supervoid, if they exist as claimed, are examples of unusually large underdense regions. The fact that we seem to be finding multiple such structures within our observable universe raises the question of whether they're truly independent anomalies or whether they're somehow connected. Perhaps the large-scale structure in our cosmic neighborhood is genuinely more extreme than typical, with both larger voids and denser clusters than average. Or perhaps our techniques for identifying and measuring voids are biased in some way that makes them appear more extreme than they really are. Another large-scale anomaly is something called the dipole repeller, a massive, underdense region located in the opposite direction from the direction in which our local group of galaxies is moving. The local group, which includes the Milky Way, Andromeda, and several dozen smaller galaxies, is moving through space at about 600 kilometers per second relative to the cosmic microwave background. This motion is thought to be caused by the gravitational attraction of dense regions in one direction, and the gravitational repulsion, or more accurately, the reduced attraction, of underdense regions in the opposite direction. By mapping the three-dimensional distribution of galaxies around us, astronomers have identified both the attractors and the repellers that are driving this motion. The largest attractor is the Shapley supercluster, an enormous concentration of galaxy clusters located about 650 million light-years away. The largest repeller is a void structure on the opposite side of the sky, located about 700 million light-years away in the direction of the constellations Centaurus, Vela, and Puppis. This dipole repeller, as it's been called, is thought to be pushing us away, or rather failing to pull us back, as we're drawn toward the Shapley supercluster. The interesting thing is that the dipole repeller partially overlaps with the direction and distance of the KBC void according to some definitions. This has led some researchers to speculate that they might be the same structure seen from different perspectives, or at least closely related structures. If so, then the fact that we're inside or near a major underdense region isn't surprising at all. we'd expect to see a large void in the direction opposite to our motion through space. But other researchers have argued that the dipole repeller and the KBC void are distinct structures that happen to occupy adjacent regions of space, and that conflating them only adds confusion to an already complex picture. Then there's the matter of something called the local sheet, a flattened distribution of galaxies that includes the local group and extends out to distances of about 30 to 50 million light-years. The local sheet appears to be a coherent structure, a sort of cosmic wall or filament, and we're embedded within it. Some cosmologists have pointed out that being inside such a structure could also affect local measurements in subtle ways, potentially adding to or complicating any effects from a larger-scale void. The point is that our cosmic neighborhood, when examined in detail, reveals a complex and somewhat unusual large-scale structure. There are underdense regions, overdense filaments, peculiar motions, and various other features that don't quite match the idealized picture of a smooth, homogeneous universe. Whether these features are genuinely unusual or just the normal kind of structure you'd expect to find anywhere if you looked closely enough is a matter of ongoing debate. One way to think about this is in terms of cosmic variance. This is the idea that if you take a finite sample of the universe, even a fairly large sample like the observable universe, the properties of that sample will naturally vary from the true universal average just due to random fluctuations. It's the same principle that applies in polling. If you survey 1,000 people about their opinions, your results will almost never exactly match the true population proportions. There will always be some sampling error. In cosmology, cosmic variance means that the average density, expansion rate, or other properties measured within our observable universe might differ from the true universal values by a few percent simply due to the luck of the draw. We happen to live in a particular patch of the universe, and that patch might be slightly denser or slightly less dense than average, have slightly more or slightly fewer large voids, and so on. This is unavoidable and doesn't indicate anything fundamentally wrong with our cosmological models. The question is how much cosmic variance we should expect, and whether the features we observe fall within the expected range, or are genuine outliers. Calculating expected cosmic variance requires cosmological simulations, and the results depend on the specific properties you're looking at and the volume you're averaging over. For something like the average density or expansion rate averaged over the entire observable universe, cosmic variance should be quite small, probably less than 1%. The observable universe is such a large volume that random fluctuations should mostly average out. But for properties measured within smaller volumes, say the nearest billion light-years, cosmic variance can be several percent or more. If the KBC void extends out to about 1 billion light-years, and we're measuring the Hubble constant using galaxies within that region, then a percent or two of cosmic variance would be expected even in the absence of any systematic void effect. This makes it very difficult to disentangle different effects and determine what's causing what. Is the locally measured Hubble constant high because we're in a void, or because of cosmic variance, or because of systematic errors in measurements, or because of new physics, or some combination of all of these? Without additional independent tests, it's hard to say for certain. What we can say is that the combination of the Hubble tension, the evidence for a local underdensity, and various other cosmic anomalies has forced cosmologists to take seriously the possibility that our location might not be perfectly average. This doesn't mean we're special in any deep sense. It doesn't mean we're at the center of the universe or chosen by cosmic forces. It just means we might be in the tail of the statistical distribution, a few sigma away from the mean. And that's enough to potentially cause problems for precision cosmology, because it means we can't blindly assume that what we measure locally represents universal values. Going forward, the key to resolving these questions will be to gather more data from larger volumes of space and to develop better theoretical models of how local structure affects observations. Projects like DSE and Euclid are already providing unprecedented views of cosmic structure out to distances of many billions of light years, far beyond any local peculiarities. By comparing the properties of structure at different distance scales, astronomers can test whether our local neighborhood is genuinely unusual or whether similar features are common throughout the universe. Similarly, improved theoretical models that properly account for the effects of inhomogeneous structure on observations will help us understand what signatures to look for and how to interpret what we see. This is technically challenging work because it requires solving Einstein's equations in complex, realistic geometries, rather than in the idealized smooth universes that are usually assumed. But progress is being made, and over the next decade, we should have much clearer answers about whether being in a void can really explain the Hubble tension, or whether we need to invoke more exotic explanations. In the meantime, we're left with an uncomfortable uncertainty. Are we typical observers in a typical location, as centuries of astronomical discovery have led us to believe? Or are we slightly unusual, occupying a position that's rare but not impossible? The answer matters not just for resolving the Hubble tension, but for understanding whether the cosmological principle, that foundational assumption that the universe looks the same everywhere, really holds up under scrutiny. And, perhaps most importantly, it forces us to think carefully about the assumptions we make when doing science and to recognize that sometimes the universe doesn't fit neatly into our theoretical frameworks. Sometimes reality is messier and more complicated than we'd like, and we have to accept that ambiguity and uncertainty are part of the scientific process. Not bugs to be eliminated, but features to be understood. The Hubble tension refuses to go away. As we move deeper into the 2020s, with better telescopes, more sophisticated analysis techniques, and increasingly precise measurements, the discrepancy between local and early universe determinations of the expansion rate has only become more pronounced. What began as a curious puzzle in the early 2010s has evolved into what many physicists now openly call a crisis, a fundamental challenge to our understanding of how the cosmos works. The latest measurements from the James Webb Space Telescope, which became fully operational in 2022, have only made things worse. Webb's unprecedented infrared sensitivity and resolution have allowed astronomers to observe Cepheid variable stars in galaxies much farther away than was possible with Hubble. This extends the cosmic distance ladder to greater distances and provides independent checks on earlier measurements. If there were systematic errors in the Hubble Space Telescope data, Webb should have revealed them. Instead, Webb confirmed and even strengthened the results. The locally measured Hubble constant stubbornly remains around 73 kilometers per second per megaparsec, while cosmic microwave background predictions stubbornly remain around 67. The gap hasn't closed. If anything, it's widened slightly as uncertainties have shrunk. This persistence has forced the cosmology community to confront an uncomfortable reality. After a decade of hoping the tension would resolve itself through better measurements or the discovery of subtle systematic errors, it's becoming increasingly clear that something genuinely unexpected is happening. Either our local measurements are being affected by something we haven't properly accounted for, or the standard model of cosmology is incomplete or incorrect, or possibly both. The void hypothesis, despite its ambiguities and complications, remains one of the leading explanations. But it's far from the only one, and the scientific literature is now filled with alternative proposals, each attempting to explain the Hubble tension through different mechanisms. Some of these proposals invoke modifications to dark energy, suggesting that it's not a constant vacuum energy as usually assumed, but rather a dynamical field that changes over cosmic time. If dark energy was weaker in the past and has grown stronger recently, that would cause the universe's expansion to accelerate more rapidly now than predictions based on early universe observations would suggest. This could potentially reconcile the different measurements of the Hubble constant. The challenge with these models is that they need to explain why dark energy would change in just the right way to produce the observed discrepancy without conflicting with other observations. Dark energy affects many things beyond just the current expansion rate, including the growth of cosmic structure, the distances to supernovae at different redshifts, and the detailed properties of the cosmic microwave background. Any modification to dark energy that fixes the Hubble tension tends to create problems somewhere else. Nevertheless, several specific models of time-varying dark energy have been proposed, with names like quintessence, phantom energy, and early dark energy. Each has its own detailed predictions and its own set of problems. The early dark energy models have received particular attention because they can potentially explain the Hubble tension without conflicting too badly with other observations. These models propose that in addition to the dark energy that dominates the universe today, there was a brief period in the very early universe, long before the cosmic microwave background was emitted, when an additional form of dark energy was important. This early dark energy would have affected the universe's expansion history in the first few 100,000 years after the Big Bang, changing the relationship between conditions at the time of the cosmic microwave background and the present-day expansion rate. The effect is subtle and requires careful tuning of parameters, but some versions of early dark energy can reduce the predicted Hubble constant from cosmic microwave background observations by a few kilometers per second per megaparsec, potentially closing much of the gap with local measurements. The problem is that early dark energy also affects other aspects of the cosmic microwave background in ways that don't quite match observations. It changes the heights and positions of peaks in the cosmic microwave background power spectrum, the statistical description of temperature fluctuations at different angular scales. Some of these changes can be compensated for by adjusting other cosmological parameters, but the fits are never quite as good as the standard model without early dark energy. As of the mid-2020s, early dark energy models remain viable but not strongly favored by the data. They can explain the Hubble tension, but at the cost of introducing new physics and providing somewhat worse fits to other observations. Whether this trade-off is worthwhile depends on how seriously you take the Hubble tension and how willing you are to complicate your theoretical models. Other proposals focus on modifications to the properties of neutrinos, those nearly massless particles that are produced copiously in nuclear reactions and barely interact with ordinary matter. The standard model of particle physics includes 3 types of neutrinos, and cosmological observations have constrained their total mass to be quite small, less than about 1/10 of an electron volt. But there are hints from some particle physics experiments that there might be additional types of neutrinos beyond the 3 we know about. So-called sterile neutrinos that don't interact even through the weak nuclear force. If sterile neutrinos exist and have the right properties, they could affect the universe's expansion history in ways that might help resolve the Hubble tension. Like early dark energy, sterile neutrinos would primarily affect the early universe, changing the predicted relationship between cosmic microwave background observations and the current expansion rate. But also, like early dark energy, sterile neutrinos tend to worsen the fit to other aspects of the cosmic microwave background data, and there's no independent evidence from particle physics experiments that they actually exist. Still, other proposals suggest modifications to general relativity itself, Einstein's theory of gravity that underlies all of modern cosmology. General relativity has been tested extensively in the solar system, in binary pulsar systems, and through observations of gravitational waves, and it's passed every test with flying colors. But all of those tests probe gravity at relatively small scales or in relatively strong gravitational fields. Cosmology requires extrapolating general relativity to enormous scales, billions of light years, and to the very weak gravitational fields that dominate the universe's large-scale dynamics. It's at least conceivable that gravity works slightly differently on cosmological scales than Einstein predicted. Numerous modified gravity theories have been proposed over the years with names like F of R gravity, scalar tensor theories, and massive gravity. Most of these theories were originally developed to explain dark energy or dark matter without invoking new forms of matter or energy. But some versions can also affect the universe's expansion history in ways that might address the Hubble tension. The challenge with modified gravity theories is that they're highly constrained by observations. You can't just arbitrarily change how gravity works without running into conflict with something we've already measured. General relativity isn't just a theory about the universe's expansion. It governs the growth of structure, the behavior of gravitational lenses, the propagation of gravitational waves, and countless other phenomena. Any modification that helps with the Hubble tension must avoid breaking all the things that general relativity currently explains successfully. As of now, no modified gravity theory has been found that can explain the Hubble tension without creating new problems elsewhere, though research continues. The diversity of proposed explanations for the Hubble tension reflects the field's uncertainty about what's really going on. If there were an obvious solution, everyone would have converged on it by now. Instead, we have a situation where multiple competing explanations remain on the table, each with its own strengths and weaknesses, and none clearly favored by the totality of evidence. This is actually a fairly typical situation in science when a field is on the cusp of a major discovery or paradigm shift. Before a breakthrough, you usually go through a period of confusion where the old framework is clearly inadequate, but the new framework hasn't yet emerged. Multiple groups propose different solutions. Everyone argues about whose approach is most promising, and progress feels frustratingly slow. Then, sometimes quite suddenly, new data or a new theoretical insight tips the balance, and consensus forms around a new understanding. The history of cosmology includes several such episodes. In the 1920s and 30s, there was intense debate about whether the universe was expanding at all, with the steady-state model competing against various Big Bang models. The discovery of the cosmic microwave background in 1965 settled that debate decisively in favor of the Big Bang. In the 1980s and 90s, there was vigorous disagreement about the universe's composition and geometry, with different groups measuring values for the Hubble constant that differed by factors of 2. The development of precision cosmology in the 2000s, particularly measurements of the cosmic microwave background and distant supernova, resolved most of those debates and established the lambda-CDM concordance model. Now, a quarter-century later, we're potentially entering another such period of upheaval. The concordance model that worked so well for so long is showing cracks, and we don't yet know whether those cracks can be patched with minor modifications or whether we need to tear down the whole structure and rebuild. The next decade will likely be decisive. Several major observational programs coming online in the mid to late 2020s will provide crucial new data that should help distinguish between competing explanations. The Vera Rubin Observatory in Chile, formerly known as the Large Synoptic Survey Telescope, began operations in 2020 and will spend the next 10 years repeatedly imaging the entire visible sky every few nights. This will produce an unprecedented dataset of billions of galaxies, supernovae, and other objects, allowing for precision measurements of cosmic structure, the distance redshift relation, and many other cosmologically relevant quantities. Rubin Observatory's wide-field camera is the largest ever built for astronomy, and its survey will be the most comprehensive ever attempted. For questions about local cosmic structure and voids, Rubin's data will be transformative. It will map the three-dimensional distribution of galaxies out to enormous distances with completeness and uniformity far exceeding current surveys. If there are systematic differences in structure between our local neighborhood and more distant regions, Rubin will reveal them. If the void hypothesis is correct, and our position within an underdense region is affecting measurements, Rubin's data should provide smoking gun evidence. Meanwhile, the Nancy Grace Roman Space Telescope, NASA's next flagship astrophysics mission, is scheduled to launch in 2027. Roman will conduct high-precision surveys of supernovae and galaxies, providing independent measurements of the universe's expansion history and the distance redshift relation. It will extend supernova measurements to greater distances and higher precision than currently possible, potentially revealing whether the discrepancy in Hubble constant measurements changes as you look farther out into the universe. If the void hypothesis is correct, you'd expect the locally measured expansion rate to gradually converge toward the cosmic average as you observe galaxies beyond the void's edge. Roman should be able to detect this transition if it exists. On the cosmic microwave background front, several next-generation experiments are being planned or are already under construction. These include ground-based observatories like the Simons Observatory and the CCAT Prime Telescope, as well as proposed satellite missions like Lightbird and CMB-S4. These experiments will measure the cosmic microwave background with even greater precision than Planck, potentially revealing subtle features or anomalies that could point toward new physics. They'll also make much more sensitive measurements of effects like the integrated Sachs-Wolf effect and the kinetic Sunyaev-Zeldovich effect, both of which are sensitive to large-scale structure along the line of sight and could provide additional tests of the void hypothesis. Perhaps most exciting are next-generation gravitational wave observatories that will come online in the 2030s. These include space-based detectors like LISA, the Laser Interferometer Space Antenna, and upgraded ground-based detectors like the Einstein Telescope and Cosmic Explorer. These instruments will detect gravitational waves from merging black holes and neutron stars at cosmological distances, and the properties of those gravitational waves can be used to measure cosmic distances independently of the traditional distance ladder. Gravitational waves are particularly promising for cosmology because they provide what astronomers call standard sirens, objects whose distance can be determined directly from the gravitational wave signal itself without needing to calibrate through intermediate steps. If you can also identify the host galaxy of the merger and measure its redshift, you can determine the Hubble constant by comparing the distance and redshift. This has already been demonstrated with a handful of events detected by LIGO and Virgo, though the current measurements are too imprecise to resolve the Hubble tension. But as gravitational wave detectors improve and the number of detected mergers grows into the thousands, standard sirens could provide the most reliable measurements of the Hubble constant yet made, completely independent of concerns about Cepheids, supernovae, or local voids. If gravitational wave measurements agree with one of the existing methods, that would strongly suggest the other method has systematic errors. If they fall somewhere in between, that might support the void hypothesis or point toward more exotic explanations. With all of these observational programs producing results over the next decade, cosmologists are cautiously optimistic that the Hubble tension will finally be resolved. But resolved doesn't necessarily mean explained in a simple or satisfying way. It's entirely possible that the answer will turn out to be complicated, involving contributions from multiple effects. Perhaps there are small systematic errors in local measurements that account for 1 or 2 kilometers per second per megaparsec of the discrepancy. Perhaps being in a moderately underdense region contributes another 1 or 2. Perhaps there's some subtle new physics involving dark energy or neutrinos that accounts for the rest. The final answer might be a messy combination rather than a single, clean explanation. This would be somewhat unsatisfying philosophically, but it wouldn't be unprecedented in science. Nature often turns out to be more complicated than our theories initially suggest, and effects that we model as simple and clean in our textbooks turn out to have multiple contributing factors when you examine them closely. The important thing is to keep testing different hypotheses, gathering better data, and refining our models until we arrive at an understanding that's consistent with all observations. Beyond the specific question of the Hubble tension, the past decade of research into voids and local cosmic structure has forced cosmologists to think more carefully about a fundamental assumption that underlies the entire field. The cosmological principle, the idea that the universe is homogeneous and isotropic on large scales, has been treated as almost axiomatic since the early days of modern cosmology. It's built into the Friedmann equations that describe the universe's expansion, and it's implicit in how cosmologists interpret almost every observation. But the cosmological principle is ultimately an empirical claim about the universe, not a logical necessity. It could be wrong, or more precisely, it could be only approximately correct, and we might be living in an epoch and a location where the deviations from perfect homogeneity matter for precision measurements. The universe is demonstrably inhomogeneous on small scales. Galaxies cluster, voids exist, structure is hierarchical and complex. The question has always been at what scale does the universe average out to homogeneity? The traditional answer has been somewhere around 300 to 500 million light-years, the scale at which structure becomes smooth and featureless when you squint and average. But recent observations, including the evidence for large voids and supervoids, suggest that structure might persist to somewhat larger scales than this. There are coherent structures approaching 1 billion light-years or more, which is getting uncomfortably close to the scale of the observable universe itself. If the largest structures are a significant fraction of the observable universe's size, then our ability to test the cosmological principle is limited, because we're trying to determine the average properties of a population from a sample that only barely includes multiple independent examples of the largest members. It's like trying to determine the average size of countries on Earth from a map that only shows 3 continents. You can make some statements, but your sample size is limited, and your conclusions might not be robust. This has led some cosmologists to question whether the cosmological principle should be treated as an assumption or as a hypothesis to be tested. If it's an assumption, then any observations that seem to violate it must be explained away or dismissed as systematic errors. But if it's a hypothesis, then we should be open to the possibility that it might be wrong, and we should look for ways to test it rigorously. Testing the cosmological principle turns out to be surprisingly difficult, because, by definition, you need to make observations over large enough volumes to average out local fluctuations. But our observable universe is only so big. One approach is to compare the properties of cosmic structure at different distances. If the universe is truly homogeneous, then the statistical properties of galaxies, galaxy clusters, and voids should be the same whether you're looking at nearby structures or distant ones. Several studies have attempted this kind of test, comparing things like the galaxy luminosity function, the abundance of clusters, and the size distribution of voids at different redshifts. Most studies find broad consistency, suggesting the universe is reasonably homogeneous, but there are some hints of anomalies that warrant further investigation. Another approach is to look for directional asymmetries. If the universe is isotropic, then it should look statistically the same in all directions. Any large-scale patterns or preferred directions would suggest a violation of isotropy and potentially of the cosmological principle more generally. Several such asymmetries have been claimed over the years. There's the axis of evil, an unfortunate name for an apparent alignment of certain features in the cosmic microwave background that seems to point in a particular direction. There's evidence for a large-scale bulk flow, a coherent motion of galaxy clusters over enormous volumes that's larger than standard cosmology predicts. There's the hemispherical asymmetry, a difference in the amplitude of cosmic microwave background fluctuations between opposite sides of the sky. Each of these anomalies has been debated extensively, with some researchers arguing they're statistically significant violations of isotropy, and others arguing they're within the expected range of cosmic variance or explainable by systematic effects. As with so much in this story, the evidence is intriguing but not definitive. What's clear is that precision cosmology in the 21st century has reached a level where we can meaningfully test assumptions that previous generations simply had to take on faith. The cosmological principle isn't just a philosophical stance anymore. It's a testable hypothesis, and while current tests generally support it, there are enough anomalies and tensions to keep the question open. If future observations reveal that our location is genuinely unusual in some way, or that the universe's large-scale structure deviates from perfect homogeneity more than currently thought, we'll need to rethink how we do cosmology. This doesn't mean abandoning the scientific method or giving up on understanding the universe. It means being more careful about distinguishing between observations, which are facts about what we can see from our particular vantage point, and inferences, which are conclusions we draw by assuming those observations are representative of the universe as a whole. It means developing more sophisticated models that can account for inhomogeneity and observer position when making predictions. It means recognizing that some questions about the universe might be fundamentally difficult to answer from a single vantage point, and accepting that uncertainty and ambiguity are inherent to the cosmological enterprise. There's a certain irony to the possibility that we might be in an unusual location. For 500 years, ever since Copernicus, the trajectory of astronomy has been toward recognizing that we're not special. We're not at the center. We're not unique. We're not privileged. Every major astronomical discovery has reinforced this lesson, pushing us further from cosmic significance. And yet, here we are, seriously contemplating the possibility that we might be in one of the largest voids in the observable universe, a location that's statistically rare and potentially affects our measurements in measurable ways. This doesn't overturn the Copernican revolution. We're still not at the center of the universe in any meaningful sense. Our location, even if unusual, is determined by random chance, not by design or cosmic purpose. There's nothing special about us that placed us here. We just happen to be where we are, and where we are happens to be in a big hole in space. If anything, this potential discovery is the ultimate expression of the Copernican principle taken to its logical extreme. Not only are we not special, but we're so thoroughly not special that even our non-specialness isn't special. We're not even in a typical location. We're in a statistical outlier, a cosmic accident, a fluke of structure formation. And yet, this accident might have profound consequences for how we understand the universe and our place in it. It forces us to confront the limits of our knowledge and the assumptions underlying our cosmological models. It reminds us that science is always provisional, always subject to revision in light of new evidence, and that the universe is under no obligation to be simple or convenient for us to study. Looking forward, the question of whether we're inside a cosmic hole and whether that affects our measurements will likely be answered definitively within the next decade. The combination of data from DSI, Euclid, Rubin, Roman, and next-generation cosmic microwave background experiments should provide enough information to map our local cosmic structure with unprecedented precision, and to test whether being in an underdense region can explain the Hubble tension. If the void hypothesis is correct, we should see clear signatures in multiple independent datasets. The locally measured Hubble constant should change as we probe different distance ranges, gradually converging toward the cosmic microwave background value as we look beyond the void's edge. The kinetic Sunyaev-Zeldovich effect should show a dipole pattern consistent with being inside an underdense region. Gravitational lensing measurements should reveal a deficit of dark matter in our neighborhood compared to more distant regions. The integrated Sachs-Wolf effect should produce characteristic patterns in the cosmic microwave background. If all of these signatures are detected with high confidence, the case for the void hypothesis would become compelling. If some are detected but not others, or if the signatures are weaker than predicted, we'll know that the void is part of the story but not the whole story. And if none of the predicted signatures show up, or if they're inconsistent with each other, we'll have to conclude that despite the evidence for some local underdensity, it's not sufficient to explain the Hubble tension, and the answer must lie elsewhere. In that case, attention will likely shift to new physics explanations, modifications of dark energy or general relativity or the properties of neutrinos. These would be more radical proposals, requiring changes to the fundamental framework of cosmology rather than just acknowledging a statistical quirk of our location. But they might be necessary if the observational tensions persist and conventional explanations prove inadequate. Alternatively, the Hubble tension might eventually be resolved through the discovery of subtle systematic errors in measurements that have so far eluded detection. This would be the most conservative resolution, requiring no new physics and no unusual location. It would mean that the concordance model of cosmology is correct as it stands, and we just needed better data and more careful analysis to recognize that. This outcome would be somewhat anticlimactic after years of speculation about voids and new physics, but it would have the virtue of simplicity. And in science, simplicity is often, though not always, a sign that you're on the right track. Whatever the eventual resolution, the journey has been illuminating. The past decade of research into the Hubble tension and the possibility that we're in a large void has pushed observational cosmology to new levels of precision and sophistication. It's forced theorists to develop more realistic models of structure formation and to think carefully about how inhomogeneity affects observations. It's reminded everyone in the field that assumptions need to be tested, that unlikely things sometimes happen, and that nature is often more complex than our idealized models suggest. It's also been a masterclass in how science works when faced with genuinely puzzling observations. There's been vigorous debate, competing hypotheses, occasional acrimony, but underlying it all, a shared commitment to following the evidence wherever it leads. No one in the field wants to cling to ideas that are contradicted by data. Everyone wants to understand what's really going on, even if the answer turns out to be complicated or uncomfortable. This is science at its best, wrestling with real uncertainty, acknowledging the limits of current knowledge, and working collaboratively to push those limits back. In the broader context of humanity's quest to understand the cosmos, the question of whether we're inside a void is just one chapter in a much longer story. For as long as humans have looked up at the night sky, we've wondered about our place in the universe. Ancient civilizations placed Earth at the center of everything. Medieval scholars inherited that view and built elaborate cosmologies around it. Copernicus and Galileo shattered that picture, revealing that we orbit the sun, not the other way around. Herschel and Shapley showed that the sun isn't even at the center of our galaxy. Hubble demonstrated that our galaxy is one among billions, all receding from each other in an expanding universe. Each of these discoveries diminished our cosmic significance, pushing us further from the center, making us smaller and less special. And yet, paradoxically, each discovery also expanded our understanding and revealed the universe to be more vast, more ancient, and more magnificent than previously imagined. The possibility that we're in a large void fits into this same pattern. It's another reminder that we're not at the center, that we're not in a privileged location, that there's nothing cosmically special about where we happen to find ourselves. But it's also a reminder that the universe is complex and structured in fascinating ways, that we're still discovering new things about its large-scale architecture, and that our understanding continues to evolve. Whether we're inside a cosmic hole or not, whether that explains the Hubble tension or not, the process of investigating these questions has deepened our knowledge and revealed new layers of cosmic structure. We've mapped the three-dimensional distribution of galaxies across billions of light years. We've characterized voids and filaments and clusters in exquisite detail. We've developed sophisticated techniques for measuring distances and expansion rates. We've pushed the precision of cosmological measurements to levels that would have seemed impossible just a few decades ago. And we've done all of this by looking out from one small planet orbiting one ordinary star in one fairly typical galaxy in what might or might not be an unusual part of space. The fact that we can ask these questions at all, let alone make progress toward answering them, is itself remarkable. We're using physics worked out in laboratories on Earth to interpret light from galaxies billions of light years away. We're using mathematics developed by humans to describe the geometry of space-time and the evolution of the universe. We're using instruments and techniques refined over generations to peer back toward the beginning of time and out toward the edge of the observable universe. The scientific method, for all its limitations and the provisional nature of its conclusions, has proven to be an extraordinarily powerful tool for understanding reality. It's allowed us to transcend the limitations of our senses, our intuitions, and our particular vantage point. It's allowed us to construct models of the universe that make testable predictions, and to refine those models when predictions don't match observations. It's allowed us to have productive disagreements about the interpretation of data while maintaining shared standards of evidence and argument. And it's allowed us to accumulate knowledge across generations, each building on the work of those who came before. As we continue to investigate whether we're inside a cosmic whole, as we work to resolve the Hubble tension and understand our place in the cosmic web, we're participating in this grand scientific tradition. We're asking the same kinds of questions that Copernicus and Galileo and Hubble asked, just with more sophisticated tools and more precise data. We're confronting the same kinds of uncertainties and ambiguities, the same tensions between different lines of evidence, the same challenge of distinguishing between what we know, what we think we know, and what we merely assume. The answers we eventually arrive at, whatever they turn out to be, will shape cosmology for decades to come. If we determine that our location is genuinely unusual, we'll need to develop new frameworks for interpreting local observations and extrapolating to universal conclusions. If we discover new physics that explains the Hubble tension, we'll need to revise our understanding of dark energy, gravity, or the universe's composition. If we find that systematic errors have been misleading us, we'll need to develop more robust measurement techniques and be more skeptical of apparently precise results. Any of these outcomes would represent progress. Any of them would advance our understanding, and any of them would raise new questions, opening new avenues for research and setting the stage for the next generation of discoveries. This is how science works. You never arrive at final, complete knowledge. You just keep refining your understanding, discovering new layers of complexity, and pushing back the boundaries of the unknown. We live in an extraordinary time for cosmology. A century ago, we didn't know that galaxies existed beyond the Milky Way, or that the universe was expanding. 50 years ago, we had only the vaguest ideas about dark matter and dark energy. 25 years ago, we hadn't yet discovered that the universe's expansion is accelerating. Today, we can measure the universe's age to within 1%, map its large-scale structure across billions of light years, and detect gravitational waves from colliding black holes. We've come an astonishingly long way in a remarkably short time. And yet, despite all this progress, fundamental questions remain. We don't know what dark matter is. We don't know what dark energy is. We don't know whether the universe is finite or infinite. We don't know whether there are other universes beyond our own. We don't know whether we're in a typical location or an unusual one. We don't know whether the laws of physics we've discovered apply everywhere and every when, or whether they're local features of our particular cosmic neighborhood. These are not small questions. They go to the heart of what the universe is and what our place in it might be. And they're questions we can actually investigate, not through armchair philosophy, but through observation, experiment, and careful reasoning. The tools we have today, telescopes that can see across billions of light years, detectors that can sense gravitational waves and exotic particles, computers that can simulate the evolution of the universe, are sufficient to make real progress on these questions. The next few decades will likely see breakthroughs that we can't yet anticipate, just as the past few decades have brought discoveries that previous generations couldn't have imagined. As we continue this journey of cosmic exploration, whether we're inside a void or not becomes almost beside the point. The real story is that we're asking the question at all, that we've developed the tools and techniques to investigate it, that we're gathering data that will eventually answer it, that we're participating in one of humanity's greatest collective endeavors, the quest to understand the universe and our place within it. We may be inside a cosmic hole. We may be in an unremarkable location. We may discover that the answer is more complicated than either of those simple alternatives. But whatever we learn, we'll have learned it through careful observation, rigorous analysis, and honest engagement with evidence. And that process, more than any particular answer, is what makes science such a powerful and important part of human culture. So, as you go about your day, as you live your life here on Earth, orbiting the Sun, in the Milky Way galaxy, somewhere in the cosmic web, take a moment to appreciate the sheer audacity of what humans have accomplished. We've looked out into the darkness and mapped the universe. We've measured the unmeasurable and characterized the void. We've taken our tiny, limited vantage point and used it to construct a comprehensive picture of cosmic history and structure. We're not done yet. We're not even close to done. But we've come far enough to ask whether we're inside one of the largest holes in space, and that alone is remarkable. The universe doesn't owe us answers. It doesn't care whether we understand it or not. But it turns out that if you look carefully enough, measure precisely enough, and think clearly enough, the universe will reveal its secrets. Slowly, gradually, with many false starts and dead ends, but eventually, the picture comes into focus. That's the promise of science, and it's a promise that's been kept again and again throughout history. Whatever we eventually learn about our cosmic neighborhood, whether we're in a void or not, whether that explains the Hubble tension or not, the knowledge will have been hard-won through decades of patient work by thousands of scientists around the world. And that knowledge, however provisional and incomplete, will be real. It will be earned. It will be our species' collective gift to future generations who will stand on our shoulders and see even farther than we can today. We're inside a cosmic hole. Maybe. Probably, to some extent. And nobody told us because nobody knew. But now we're finding out, and the story of how we're finding out is as fascinating as the answer itself. Thank you for watching,